So today's lesson is about the same kinds of calculations, thermochemistry or thermodynamics, that we've been using. We're going to move now into the kind of calculations that are used very often in a real lab in an area called calorimetry. So let's start with the homework problem you were given to do last night. 2.47 sample of ice, 2.47 grams sample of ice at -5 degrees is heated until it's liquid at 25 degrees C. How much heat energy was used? What's happening here is we're going through a phase change. Here's the heating curve for water we looked at yesterday, and we're starting with ice at -5 degrees. So that's down here. Here's 0 degrees on the temperature scale on our vertical axis. 100 degrees is here, and it's below this. So this is the range where we have ice. We're going to heat or cool ice, and ice can't get any warmer than 0 degrees C. There's 0 degrees C right there. We can't be any warmer than that. So our temperature change is from -5 to 0. It can't get warmer than that. Then we're going to melt that ice along here, but notice the temperature doesn't go up at all during that phase change. So we need a different equation for that. So while we're heating up the ice from -5 to 0, we're using this equation. Q equals mass times the heat capacity, or specific heat it's sometimes called, times the change in temperature. And then when we're going through the phase change, we're using Q equals mass times the heat of fusion, or the enthalpy for the melting or freezing of water. Down here it says melting ice or freezing water. And then finally, once we get it all melted, then we can heat it up again, heat up the liquid water from 0 degrees C, because water is not going to be liquid below 0 degrees C. Heat it up until we get to that 21 degrees C somewhere along here. And so we need 3 different equations. In this range, where we're heating up the water, we need this equation. And what you do is the math for those 3 equations, then add everything up. All right, back to our question then. We've got 3 different stages here we're dealing with. For the ice, we've got Q equals mass times the heat capacity times the change in temperature. And the change in temperature is always temperature final minus temperature initial. In that range, temperature final is going to be 0 degrees C, because ice in the water in the form of a solid, ice, can't be any warmer than 0 degrees C. It's going to go from -5 up to 0, and then it starts to melt. So the ice can't be any warmer than that. Our final temperature there for that range is 0.00 degrees C. And I know on the heating curve for water, it just says 0, like it's one significant digit, but that's essentially, or can be thought of as an absolute value. You can put as many decimal places or zeros after the decimal places you want. 0.000000. We don't really need all those. But you could use as many zeros as necessary. All right? And so the initial temperature is -5 degrees. So we're going to have a -5 degrees, but we're subtracting that. Okay? So it's minus a -5 degrees C. And when you subtract a negative number, it's like or thought of often in math as adding. And so we get 5.00 degrees C. It's a positive number. So we got what plugs in here. Okay? So we're going to put that 5 degrees in here. We got the mass, and the mass for all these problems is 2.47. The amount of water, the mass of the water doesn't change. Grams here. The specific heat for the ice is on the front page of your test references. Okay? Here's the specific heats for liquid water, right there. For gas or steam, there it is, and for solid water or ice is right here. It's also showing you what the heat of fusion or heat of, or the enthalpy of fusion is for water, and the fusion heat is the heat put in to melt a sample of ice, or taken out to freeze a sample of water. It's the same value, and that number is 334 joules per gram. Okay? So we'll get back to those other numbers in a minute. Right now we just need that specific heat for the ice. And so here's our solid ice here. Here's the number we need. Here's the value with all those units of measurement. So 2.05 joules per degree C per gram. And all those have to be there, and I'll show you why in a minute. And our change in temperature is 5.00 degrees C. All All right, so we can cancel out units now. This is the beauty of dimensional analysis. It helps you to see whether you've set up your problem correctly. So because I have grams on the top and grams on the bottom, I can cancel those. I've got degrees C on the top and degrees C on the bottom. I can cancel those. What I have left is joules, and joules is a measure of energy. But I'm looking for energy. Q means heat energy. So joules, the energy unit, matches up with the dimension I'm looking for, and I know I've set up the problem right. Now, sometimes we need more things than that, but for most of the time in high school chemistry, this works out just beautifully to see whether you set up your problem right. When you get to this point, you can check, and you should always check when you get to this point. Now, remember, it's required that you write out the equation you need first with all these measurement dimensions in them, and then you plug in the numbers you have with the measurement units and cancel. All right, now we're ready to do the math. Now we multiply these together. Let's put the calculator up so you can see me doing that. Okay, so 2.47, let's just do it again for you so you can see me do it. 2.47 times 2.05 times 5.00. Whoop, 5.00. And we get this number here, okay? So 25.3175. And you have to write all those digits down, okay, with the units of measurement that go along with it. There's our unit of measurement. And then we're going to round off to the correct number of significant digits. We're going to look at this problem and find the measured or calculated numbers here with the least digits and match the least digits in our final answer. So this measured number has 3 significant digits. Excuse me. This calculated number has 3. This calculated number has 3. So we want the final answer to be 3. We're going to count 1, 2, 3 and underline all the insignificant digits. Draw an arrow to show that we're rounding off. That's required. Underlining and arrows are required just as the cancellation is required. Underline the insignificant digits and round off to 25.3 joules. And that's the energy used or put into our sample of ice to get it up to the point where it starts to melt. Okay? What we're ready to go to now is the point where we're changing from ice into water, the melting. Okay, so this is the melting stuff that's going on here. Okay? And we'll go back and look at that heating curve for water so we can see the equation. So during that phase change, when you're melting ice or freezing water, see down here at the bottom it says melting ice or freezing water. That's our phase change. We're using this equation because there's no temperature change. We can't use a delta T or temperature change when there's no temperature change. That would just give us a 0. And we're not doing that. We're adding heat to it to melt it. So we're using this equation. So Q equals mass times that enthalpy of fusion, or heat of fusion, or heat of melting, and that number is on the test references again. Click over here. Here's our heat of fusion number. Heat of fusion is the same as heat of melting, and it's this number right here. We're using grams. We're going to use this number right here with grams in it. 334 joules per gram. So our mass is the same, we said, 2.47 grams. Our heat of fusion, 334 joules per gram. Put this over 1 so we can see that we can cancel out grams. We're left with joules. Joules measures heat energy. We know we probably set it up right. All we're going to do is put in the calculator. So 2.47 times 334, and we get 824.98. $824.98 joules is what I have left. I've canceled out everything else. Got to round it off to the correct number of significant digits. I've got 3 digits here and 3 digits here, so we want 3 digits here. Underline to show we're rounding off those 2 digits. Draw an arrow to show we're rounding off. 8.25 joules. I'm sorry, 825 joules. Let's take out that decimal place. 825 joules. Okay? And that's for the melting. Now we're ready to go through that range where we are heating up the water. Okay, so we've gotten all the water melted here in this phase change region on our heating curve graph. Now we're ready to heat it up. And so we're going to be using this equation where there's a temperature change there. Okay? All right, so for water then, we've got Q equals mass times specific heat times the change in temperature. The mass is the same, 2.47 grams over 1. The specific heat for liquid water is on your test references here, 4.18 joules per degree C per gram. It says specific heat, and there's an L. Now, this points out why we want to use a capital L when we write liters and milliliters and such, because you can't really look at that unless you just know what it means and tell that that's an L. It could be a number 1 or it could be a capital I. But you should know if this is gas and this is solid, that has to be liquid. So our liquid specific heat for water is 4.18 joules per degree C per gram. And then our change in temperature, we got to calculate. Change in temperature here, temperature final minus temperature initial. It's always necessary for me that you write out the equation we're going to be using so that I know you've chosen the right equation and you're solving the right problem. If you don't write out the equation, I can look at your work but can't tell what you're doing. So write everything down. Not only does it tell me what you're doing so I can help you, but it helps you to stay organized as well. So make sure you write out the equation before you solve the problem. Now, what's our final temperature here? We're trying to get to 25 degrees, and it's liquid water, so that's our final temperature, because this is the range where we're heating up the water. Final temperature is 25.00 degrees C, and the initial temperature is the temperature we started at once we melted it. Let's look again at our heating curve. Once we melted it, we're at 0 degrees C. Here's 0 degrees C on the vertical axis here. And we're right here. We're starting here and going up. So we're starting at 0 degrees C. And so the initial temperature we're going to subtract minus 0.00 degrees C. That just gives us 25 degrees. Okay, and that's our temperature change for the liquid water. This was our temperature change for ice. Okay, this is our temperature change for liquid water. All right, again we cancel, and we do the math. And you get 258.115 joules. Look at the digits we have in these numbers, this measured number and 2 calculated numbers. This number here has 4 significant digits. Trailing zeros, if there's a decimal place, are significant. So the 2 non-zero digits are significant, and these 2 zeros are significant for 4 significant digits. But you're going to look at the measured or calculated numbers with the least digits. And this one has 3, and this one has 3, so we want our final answer to have 3. So we're going to underline the last 3 digits, 3 significant digits here, 1, 2, 3, and underline the insignificant digits, 1, 2, 3, and show an arrow to show we're rounding off, and write 258 joules. Okay? Now, that gives us 3 different values for the heat energy. The one for liquid water, the one for melting here, and the one for ice. And all we do is add those together to find the Q total. The total amount of energy used is the sum of all the other Q's, okay, during all these changes, heating up and phase changes, okay? So what we want to do is take the 3 Q's, 25.3 joules, 825 joules, and 258 joules, and add all those up. Okay, and using the system that I've taught you, you want to always add or subtract vertically, because the way that I've taught you to handle or figure out significant digits when you're adding and subtracting is any numbers to the right added to an empty slot or subtracted to or from an empty slot result in an insignificant digit, and you round it off. So there's empty slots here and here. You can't write zeros here. I know that's what you've been taught in math, but we don't do that in chemistry because writing a 0 here, a decimal and 0, would indicate that this number, this measurement, or this calculation is more precise than it really is. And we don't want to lie about precision. We want to be honest about precision. So you can use an arrow like I did to keep your slots all lined up, but please don't put in zeros there because that would be intellectually dishonest in a chemistry setting. So our answer here is 1108.3 joules, but that's an insignificant digit right there. So we underline it, draw an arrow to show we're rounding off. Our final answer then is 1108 joules. And you don't have to write it, but it's always good to write it and say that is our Q total. Okay? And so that's how you solve the homework problem. Now then, let's take a look at a little bit of theory. Okay, if you'll work with me here just a minute. I want to talk about how it is we figure out the amount of heat energy that's contained in a system or being moved around in a system, and this is a process called calorimetry. So we're going to talk some theory here for a minute. Whatever it is that we're testing, whether it's the chemical we're testing, the chemical reaction we're testing, or some substance we're testing, whatever it is we're interested in terms of the energy contained in it or moving around from it, we call that our system. And it might be a rock. If I want to know how much heat energy is transferred from a rock, the rock is a system. Okay? So that's our system. Anything around that system, that's the surroundings. So if the energy is leaving, it's leaving to the surroundings. We just call that surroundings. I know that's a big fancy word, surroundings, right? That's a joke. It's not a big fancy word. Surroundings, everybody should know what that means. Okay? So if we're moving energy from the system out, we're moving it from the system to the surroundings. If we're heating up the system, that energy comes from the surroundings. It has to come from somewhere because the total amount of energy in the universe is constant. What's the universe? The universe is all this. The universe is the system and the surroundings all together. Okay? Now, we can't measure the amount of energy in the universe or the energy change in the universe, but we can limit our area of the universe for testing purposes. Okay? We can kind of insulate a certain section of the universe. Okay? And that's the basis of what we call calorimetry. And in calorimetry, we want to isolate a section of the universe and make it our little mini universe for our testing. And so a calorimeter is very simply a closed system or closed universe, okay? And we're just going to test what's inside, all right? So this should be insulated. That's the idea. We insulate from the rest of the universe so we can see just what's happening right here. So our system that we're going to test is usually put inside of this, okay? And anytime we move the energy out of there, it's going to go into this little mini closed universe here for us. It's not really the universe, but we kind of use it like that. And so we can measure the energy change here in order to figure out what's going on between the system and the surroundings. Okay, so this is our surroundings inside. And all together, this is our closed, sectioned off part of the universe for purposes of testing to be able to figure out what's going on. Usually, not always, but usually calorimeters are filled with water because water's so ubiquitous and it works really, really well for figuring out how energy is moving around. So if we're moving energy from here into the surroundings, we can measure what's happening in the water and calculate what's going on in the system in whatever we're studying. If it's a rock, it's a rock. In the case of the lab, we're going to do, it's how the chemical we're testing is interacting with the water molecules. We're still testing what's changing in the water to figure that out. So let's look at a calculation then that involves this sort of thing. So here's our practice problem. A calorimeter contains 100.0 grams. So we have to know the mass of the water in our calorimeter. And when we do the lab, you have to make sure you measure the mass of the water in the calorimeter. And then we're going to start with, in this case, an initial temperature of 30 degrees C, 30 degrees centigrade. Okay? Now, let's see here. This is not the problem I meant to start with. Where did I write that down? Okay, I don't want to start with 30 degrees. I want to start with, let's start with 21 degrees here instead of 30 degrees. Not that it matters a lot. We can start with this. It's not that big a deal. And let's go ahead and put a second 0 here and give it 4 significant digits, okay? .00 degrees C for the initial temperature of water. We're going to put in there a rock. Let's just use a rock, okay? So a rock with an initial temperature of 80 degrees. It's placed in the calorimeter. Then at what's called equilibrium, this is the point where the temperature of the water and the rock become the same. I mean, just imagine for a minute, you've got something hot and you throw in some water. The hot thing cools down. It also turns out that the water heats up. And so if you leave the substance you're putting in that water there long enough, what happens is the water and the substance in there become the same temperature. They reach equilibrium. That's what that word means, just reaching the same, being the same, coming to the same point. All right? Later in the semester, we'll talk about something called a dynamic equilibrium. But right now, we're just coming to a same temperature, an equilibrium temperature. Okay? So at equilibrium, the water and rock are at 22.00 degrees C. Okay, that's our equilibrium temperature. What we're going to calculate is what is the heat capacity of the rock. C-A-P-A-C-I-T-Y of the rock. Okay? So going back to our image we drew a moment ago, we looked at how energy goes from one place to the other. We have energy that's going to leave the system and go to the surroundings. Or we have energy in the surroundings that's going to the system. It's going one way or the other. The amount of energy in the universe doesn't change. We just move it around. Okay? Well, if that's the case, then whatever amount of energy that's lost by the system is going to equal the inverse, the negative of the energy lost by one has to be the negative of the other. If we're losing energy here, we're gaining it here. Whatever energy we're losing here, we're gaining here. Or if we're moving energy the other way, whatever energy is lost here goes to here. Well, that means our Q, which is the amount of energy moved around, Q from the, let's put the rock on this side. It really doesn't matter. One's just the negative of the other. The rock is equal to the negative Q of the water. Okay? So if we calculate Q, we can find the Q of the other. It's just a negative. Just change the sign from positive to negative. Or if it's a negative term that you calculate, then you're going to change the sign to positive. Just change the sign. Okay? Well, both of these are going through a temperature change, and there's no physical state change. And if we go back to our heating curve for water, and all substances behave in a similar way. This is just for water, but rocks behave the same way. As long as all we're doing is changing the temperature, okay, then we use this equation right here. Q equals mass times the specific heat times the change in temperature. Okay? So we've got two of these to deal with here. We've got the temperature change for water, and we've got the temperature change for the rock. What we don't know is the specific heat for the rock. We're going to find it. So, let's start with the water first. Okay, we could either write this like as I said a moment ago. We could write like this because the negative Q of the rock is equal to the positive Q for the water. It's just a change in sign. Either one of those works. This or this, either one. Okay. Let's find the Q for the water first because we have everything we need to do that. Okay, so Q, the heat energy moved around, heat energy change for the water is equal to the mass times the specific heat times the change in temperature. Change in temperature is equal to temperature final minus temperature initial. Our final temperature for the water at equilibrium is 22 degrees C. Our initial temperature for the water is 21 degrees C. I should have put an extra 0 on there, shouldn't I? Got to keep up with the significant digits. And so we're going to subtract initial temperature from final temperature, and you get a 1 degree temperature change. Okay? The mass for the water, got to be careful about which one we're working with because we've got two different masses here. We've got a mass for the rock and a mass for the water. Hope I didn't put in the mass for the rock. The rock's mass is going to be let's say it's 5.00 grams, okay? That's our mass for the rock. The mass for the water is 100 grams. Our specific heat for water, it's on your test references. Liquid water specific heat, 4.18 joules per degree C per gram. And the change in temperature is 1 degree. Okay? Now you could do the math. So we're going to pause the video. I'm going to ask that whoever's watching this, pause the video a minute, let you solve the problem, and then look at the solution. Alright, so the solution is we're going to cancel out units. We can cancel. Grams on the top can cancel grams on the bottom. Degree C on the top can cancel degree C on the bottom. Okay? And so we just do the multiplication now. Bring up the calculator. 100.0 times 4.18 times 1.00. I bet you already know what that answer is. Okay? You probably could have figured that one out in your head. That one's pretty easy. Okay? So 418 is our answer. Look at the significant digits. This calculated number here has 3 significant digits. This calculated number has 3 significant digits. This measured number has 4, and of the measured and calculated numbers, 3 here and here. 3 is the least. We want 3 here. We don't have to round off because it's already in 3 significant digits. Okay? Now then, what's happening with the rock? Well, the Q for the water is the negative of the Q for the rock. Okay? So let's change the sign here, okay, and say negative 418 joules is equal to the Q for the rock. Okay? The negative of the water equals the Q for the rock, and the Q for the rock is going to be calculated with this same equation. Mass times specific heat times the change in temperature. I really should have written out Q here and then plug everything in. Let's do that. We're going to do that. We're going to put that negative 418 joules in there. But this is the Q for the rock. So we're going to keep everything nice and neat. Okay. And this is our energy change for the rock. And we just know from what we calculated for the water is the negative sign. So we're going to plug it in now at negative 418 joules equals the mass of the rock is 5 grams. Okay. The specific heat we don't know. And the change in temperature for the rock we have to calculate. Change in temperature. Temperature final minus temperature initial. The final temperature for the rock is the same as the final temperature for the water because the final temperature for the water and rock are at equilibrium. So the final temperature is 22 degrees C. Okay. The initial temperature of the rock is 80 degrees. So we're going to subtract 80 degrees. Okay. So 22.00 minus 80, and we get negative 58. All right. Now we really don't have to put all these over 1. Because just putting them over 1 is the same number. Well, to make our math a little simpler, I'm going to take out the fractional part of this. We've been putting it over 1, but in this case, if we don't need it, we don't need it. Might make our math a little bit easier here. Now, I know in math, you've been taught how to solve these kinds of problems before. I'm going to teach you a slightly different system. It's really the same system, just written down a little bit differently. What I want to do, and we're going to be using the same process anytime you're working with an equation like this. Okay, we are given an equation that you plug numbers into. We'll be doing this again when we get to the gas laws unit. Anytime you're starting with an equation like this, you need to write out the values in a list. I didn't really do that here, but it's a good idea to do that. Write out the values in a list so you can keep up with it. Write out the equation that is required. Here's an equation, here's the equation, you have to write it out. Then plug in the values as I did here. Then the next step is a little bit different than maybe you've done it in math. What I want to do is to get specific heat or heat capacity here on this side of the equation all by itself. And to do that, I want to mathematically remove these two values. Well, if I'm multiplying here, the way that I mathematically remove those two values is to divide by those two values. I'm going to divide by 5.00 grams times negative 58.00 degrees C. But here's the key. You can do this if you also do it to this side. So remember this. What you do to one side of the equation, you must do to the other. I know you've been doing that in math. You might not have called it exactly the same thing, but that's the way it's done. If you do it to this side, got to do it to that side. Got to be fair, okay? All right, so we're going to divide the same thing on this side, 5.00 grams times negative 58.00 degrees C. What that does is cancel the 5 grams. That all cancels. It's exactly the same. It can cancel out. The negative 58 can cancel here. Over here, we're ready to do the math. So we're going to take, now this is another thing, a little fast way to do the math in a chemistry class that I'm going to teach you. Okay? I'd like you to get in the habit of doing it this way. We're going to take this negative 418 joules and divide by this number, hit enter or equals, and then take the answer and divide by this number. It's fast on the calculator that way, and we do it a lot in this class. Let's try to get in that habit of doing it that way. All right, so negative 418, whoop, didn't get him all the numbers. Okay, we're going to do I got to change the sign. That's a good point here. Stop a minute and look. That right there, that's a subtraction symbol. This is a change of sign symbol. If I want a negative number, I got to click there. A negative 418 divided by 5.00. Okay, so that we're doing this first part. Negative 418 joules divided by the 5 grams here. Okay, I'm going to hit enter, and we get this number. Then I want to divide by the second number on the bottom. Okay, the negative 58.00. So if I hit my divide key, it automatically says I'm going to take that last answer up here and divide by something. Most calculators do that. It's a little fast way of getting it done. So all I have to do is put in that second number, that negative 58.00. And there's the answer we're seeking. Okay? 1.44138. Go back over here and we can see that we have units of joules divided by grams divided by degrees C. And if we go back up here and look, all of our specific heats had those units. All of our heat capacities had those units. So that's good. That's what we want. If we have set it up right, the units of measurement we have at the end should match what we're seeking. We're seeking specific heat or heat capacity, and that always comes in joules, at least in this class, always comes in joules per gram per degree C, or joules per degree C per gram. You can switch around grams and degrees C, it doesn't really matter. Joules per gram per degree C. Now we're ready to round off, and this is equal to the specific heat. Okay? We've got 3 digits in this number, 3 here and 3 here. We want 3 here. 1, 2, 3. Underline the last 3 digits, which are insignificant. Round off. Have to use an arrow to show a rounding off. And our final answer then is 1.44 joules per gram per degree C. Okay? All right. Let's solve a problem on your own now. Find a learning partner to work with you. And between the two of you, I want you to solve this next problem. Okay, so here's our problem. A calorimeter with 100 grams of water at 30 degrees C has a 10-gram sample of aluminum at 3 degrees C placed in it. If the equilibrium temperature is 30.6 degrees C, what is the heat capacity or specific heat of the aluminum? So I'm going to ask the teacher, or you if you're looking at this individually, to pause the video now. You choose a learning partner, and between you and your learning partner, struggle through the process, figure it out, set it up, and solve the problem. This is not a chance for you to just sit back and twiddle your thumbs and wait for the answer. You're not learning as much here as if you are struggling through the answer. When you get on a test, you're going to struggle through the answer there. If you practice struggling through the answer now, you're more likely to be able to struggle through the answer when you get to the test. So do not sit back and wait. Get the answer done, okay? Find other people in the class who can help you and solve the problem. This is how you practice solving problems so you're successful when you have to use it. Okay? So pause the video now and solve this problem, please. Okay. So let's make sure we sort of organize things here for ourselves, okay? Let's list out everything that's here. This is what I want you to do when you solve problems for me, when you have an equation that's involved. And this is going to involve equations. We have water and we have aluminum. And if you remember, when we were looking at the nature of science. We looked at how science is put together, how it's organized, how science gets done. And there was an organizational chart that showed that. We said that we weren't going to think about science in terms of the scientific method in here. We're going to look at it in terms of this organizational system here, okay, where we're trying to figure out how is it that science gets done, what is the goal, what is the main aim of science. And the first part of this in the upper left, it's not really a first because it's continuous in a kind of wheel, is organizing what we know. Well, we're kind of imitating that here when we're organizing what we know. So we're going to organize this stuff. For the water, we've got a mass of 100.0 grams. Okay? Let's see, we have a temperature of 30 degrees in the beginning, so our temperature initial is 30.0 degrees C. Okay? Our aluminum, we're starting with a mass of 10.0 grams. And we're starting at 3.0 degrees C as our initial temperature. 3.00 degrees C. Okay? At equilibrium, the temperature is going to be 30.6, which is both of these. Both of these are going to have the same temperature at equilibrium. That's what happens. You put a sample of something in water, and the two of them are going to eventually reach the same temperature. So our final temperature is going to be 30.6 for both. Okay? Well, what else do we know? We know the specific heat for water. Liquid water specific heat is 4.18 joules per gram per degree C, and it's on your test references. Liquid water, there's the specific heat. Okay? What we don't know is the specific heat for the aluminum, but that's what we're trying to find. So I'll put a question mark there. Okay? So since we know all these values for water, let's find the Q for water first, just to make it easier on ourselves. Okay? The equation we need for water, and again, don't save on the pencil lead. By the way, your pencil doesn't have any lead in it. Many, many, many years ago before you were born, pencils had lead in it. Now they have graphite. So don't save on the graphite in your pencil. Write this stuff down because this is how you organize. It's also how you figure things out. If you have so many things on the piece of paper that you can't figure out what you were doing, then you weren't organizing. Label it. Put it down on paper. Don't leave things off. So for water, we're looking at a temperature change, and we're looking for the Q, the energy change here. All right, that's what we're going to need to find the specific heat. Q equals mass times the specific heat, or heat capacity, times the change in temperature. Change in temperature is always temperature final minus temperature initial. Our final temperature is going to be 30.6 degrees C. Our initial temperature is going to be 30.0 degrees C. We're going to subtract, okay, and we're going to get 0.6 degrees C change. Okay? Now we're ready to plug all those values in there, okay, that we have. We have a mass of 100 grams. We have a specific heat of 4.18 joules per degree C per gram. And you can put grams in front of degrees C, doesn't really matter. Change in temperature, 0.6 degrees C. All right, we're going to do the math. Let's see here, calculator. Let's erase these other things we did in the last problem. And put in 100.00 rather, times 4.18 times 0.6, and we get 250.8. All right. Now we're going to cancel out grams and degrees C. If you're on the top and bottom, you can cancel them out if they're the same. So what we have left are joules. Joules measure heat energy. We know we set it up right. We need joules in our final answer. We really need only one significant digit here. And we could do that I want to kind of wait till the end to kind of see how it's all going to come out, okay? And figure out we're going to have only one significant digit at the end when we're finished, okay? All right, so that's what's happening with the water part of things, all right? So we know that, let's go back to our image where we looked at how energy moves around, okay? Whatever energy is leaving the aluminum is gained by the water. Whatever energy is leaving the water is gained by the aluminum. Okay, it's got to move from here to here or here to here. Can't go anywhere else in a closed system like this. That's what we're trying to work with, is we're trying to imitate a mini universe to figure all this out. Okay, so the energy, let's see, this is the energy lost by the water. Let's see, the water is going to be hotter than this, so the aluminum is going to heat up. Let's say the aluminum is going to gain the energy, aluminum. I mean, not that it matters, because it's just a negative of the other. It doesn't matter whether you put the negative on this side or this side, but we're going to do it this way. We'll say this is the positive, this is the negative. It would work out the same way if this were the negative and that was the positive, okay? But for the aluminum then, we've got Q equals mass times specific heat times the change in temperature. Change in temperature, temperature final minus temperature initial. Final temperature is 30.6 degrees C. Final temperature is going to, initial temperature, we're subtracting initial temperature, is 3.00 degrees C. And so what we're going to get here is, let's go to the calculator. Bring up the calculator. There we go. All right, so 30.6 minus 3.00, and we get 27.6. There is an empty slot here. You got to know that you're putting that zero down there and rounding it off. Okay? So 27.6 degrees. Got to be smarter than the calculator. The calculator won't give you the zero. You need to know that zero's there. And this is our change in temperature for the aluminum. Okay, we're going to plug all that in. We've got I need to go to another sheet of paper, so let me kind of move this over. Hopefully you're writing a little smaller than this. Let's plug in our Q. Our Q is the negative of whatever we calculated the Q for the water to be. Our Q here for the aluminum is going to be the negative value of whatever we got for the water. So this is a negative 250.8 joules is equal to the mass. Okay, the mass of the aluminum is 10 grams. We are trying to find the specific heat. We don't have it. And then the change in temperature we just calculated to be 27.6. Okay, this change in temperature is 27.6 degrees C. And we want to get Cp by itself. I'm going to divide both sides by everything but the unknown. Okay? And whatever we do to this side, got to do to the other side. 10.0 grams times 27.6 degrees C. This allows us to cancel all of this and all of this. We've got specific heat by itself, which is what we're trying to find. And we know that specific heat comes in units of joules per gram per degree C, and we have that. So we're ready to just put it in the calculator now. All right, so before we go any further, I just realized I made a small error here. When we take 30.6 and divide by 30, that should be a negative 6, which means there's a negative 6 here, and this is a negative number, which then makes this number not negative, because we're going to change the sign here. This should be a positive. Okay? Anyway, So now we're ready to put that in the calculator. So 250.8 divided by 10, 10.0, not 10.00. There we go. Enter. And then divide that by 27.6, and we get this number right here for the specific heat. 0.908696 joules per gram per degree C. Okay, we're going to round it off. Remember, this only had one significant digit up here. We just didn't round it off when we were up here in the beginning, okay? We should have rounded it off to one significant digit, so we're going to end up with one significant digit here, okay? I don't need an equal sign. Well, I do, because it's specific heat on this side. And then we're going to round it off to 0.9 joules per gram per degree C. And there's our final answer. 0.9 joules per gram per degree C. What is the heat capacity of a sample of unknown substance? If the sample weighs, not weights, but weighs 4.00 grams, and initial temperature of, let's say, 72.00 degrees C. The calorimeter is filled with 50.00 grams of water at 10.00 degrees C, and the equilibrium temperature is 12.00 degrees C. Okay, so there's your homework problem, and we're ready to get started.